What is the main motivation behind the proposed method in the paper?
The main motivation behind the proposed method in the paper is to address the existing limitations in controllable text-to-image generation models. The paper aims to enhance the controllability of image generation by improving the consistency between input conditional controls and the generated images. The proposed method focuses on optimizing controllability at the pixel level through a cycle consistency approach, utilizing pre-trained discriminative models to extract conditions from generated images and optimize cycle consistency loss. By explicitly optimizing controllability in the pixel space, the paper aims to overcome the challenges faced by existing methods in accurately generating images consistent with input conditions. The goal is to provide a more efficient and effective approach for training controllable text-to-image models, ultimately improving the quality and controllability of generated images under various conditional controls.
How does the paper address the challenge of achieving precise and fine-grained control in text-to-image generation?
The paper addresses the challenge of achieving precise and fine-grained control in text-to-image generation by proposing ControlNet++, which significantly outperforms existing methods in terms of controllability across various conditional controls. It introduces a novel approach that utilizes pre-trained discriminative models to extract conditions from generated images and optimize cycle consistency loss for better controllability. By explicitly optimizing controllability at the pixel space level, the model disrupts the consistency between input images and conditions by adding noise to training images, leading to more efficient reward fine-tuning without the need for multiple sampling steps. This approach ensures that the generated images maintain good consistency with input conditions, enhancing the model's ability to follow conditions during generation. Additionally, the paper demonstrates the effectiveness of ControlNet++ through a unified and public evaluation of controllability under various conditional controls, showcasing superior performance compared to existing state-of-the-art methods.
What specific method is proposed in the paper to improve controllability in text-to-image models?
The specific method proposed in the paper to improve controllability in text-to-image models is to employ pre-trained discriminative models to extract the condition from generated images and optimize the cycle consistency loss for better controllability. This method involves translating images from one domain to another, from input conditional controls to output generated images, and back again to ensure consistency with the original input conditions. By explicitly optimizing controllability at the pixel space level through cycle consistency loss, the model aims to enhance performance in generating images that align closely with the specified input conditions. Additionally, the paper introduces an efficient reward fine-tuning strategy that disrupts the consistency between input images and conditions by adding noise to training images, leading to single-step denoising for more efficient reward fine-tuning without the need for multiple time-consuming samplings.
How does the proposed method differ from existing works in terms of optimizing controllability?
The proposed method differs from existing works in terms of optimizing controllability by explicitly optimizing controllability at the pixel space level for better performance. Unlike existing methods that implicitly achieve controllability by introducing conditional controls into the latent space denoising process, the proposed method employs pre-trained discriminative models to extract conditions from generated images and directly optimizes the cycle consistency loss. This approach ensures that the predicted conditions and input conditions are consistent, enhancing controllability. Additionally, the method disrupts the consistency between input images and conditions by adding noise to training images, leading to single-step denoising for efficient reward fine-tuning. This strategy avoids the time and GPU memory overheads caused by multiple sampling steps, making the reward fine-tuning process more efficient. By combining training loss with reward loss, the proposed method guides the model on how to sample at different time steps, to generate images consistent with input conditional controls, ultimately improving controllability without compromising image quality.
What is the significance of modeling image-based controllable generation as an image translation task?
Modeling image-based controllable generation as an image translation task is significant because it allows for explicit optimization of controllability at the pixel space level, leading to better performance. By employing pre-trained discriminative models to extract conditions from generated images and optimizing cycle consistency loss, the method ensures that the generated images align closely with the input conditional controls. This approach enhances controllability by focusing on the consistency between input conditions and generated images, providing a clear and effective strategy for improving controllability in text-to-image models. Additionally, by formulating the cycle consistency loss as a per-pixel classification loss between input and predicted conditions, the method ensures precise and fine-grained control over the generated images. Overall, modeling image-based controllable generation as an image translation task offers a systematic and efficient way to enhance controllability in text-to-image models, ultimately improving the quality and accuracy of generated images.
How does the paper propose to optimize controllability at the pixel space level?
The paper proposes to optimize controllability at the pixel space level by employing an efficient reward fine-tuning strategy. Instead of diffusing from random noise to obtain the final image, the proposed method adds noise to the training images to disturb their consistency with input conditional controls. By disturbing this consistency and performing a forward process, the model is guided to generate images that can reconstruct the consistency, thereby enhancing controllability. This approach avoids the time and GPU memory costs associated with multiple sampling steps. The one-step efficient reward strategy utilizes the disturbed images to directly predict the original image, which is then used for reward fine-tuning. This method significantly improves efficiency during the reward fine-tuning stage and ensures that the original image generation capability is not compromised. The total loss function combines the training loss and the reward loss, with a hyperparameter to adjust the weight of the reward loss, guiding the model on how to sample at different time steps to generate images consistent with the input conditional controls.
What are the contributions of the proposed method according to the paper?
The contributions of the proposed method ControlNet++ as outlined in the paper include 1. New insight, revealing the shortcomings of existing controllable generation methods in terms of controllability, highlighting the significant deviation of generated images from input conditions and the lack of a clear strategy for improvement. 2. Consistency feedback, introducing the concept of using pre-trained discriminative models as visual reward models to enhance the controllability of controllable models in a cycle consistency manner. 3. Efficient reward fine-tuning, proposing an efficient reward strategy that disrupts the consistency between input images and conditions by adding noise to training images, leading to single-step denoising for efficient reward fine-tuning, thereby avoiding time and memory overheads associated with multiple sampling steps. 4. Evaluation and promising results, providing a unified and public evaluation of controllability under various conditional controls and demonstrating that ControlNet++ outperforms existing methods comprehensively in terms of controllability. 5. Efficiency improvement, addressing the efficiency issues related to reward fine-tuning by avoiding multiple time-consuming samplings and excessive GPU memory usage, thus enhancing the overall efficiency of the controllable generation process. 6. Enhanced controllability, achieving significant improvements in controllability across different conditional controls compared to state-of-the-art methods, such as achieving a 6% RMSE improvement for the depth map condition. 7. Preservation of image quality, demonstrating that the proposed method enhances controllability without compromising image quality as evidenced by superior fit values compared to existing methods. 8. Clip score improvement. Achieving comparable or superior clip score outcomes on various datasets, indicating improved controllability while maintaining the proficiency of the original text-to-image generation model. 9. Effectiveness in discriminative models, showing that the generated images by ControlNet++ can significantly enhance the performance of discriminative models, such as segmentation models, when used for training, highlighting the practical benefits of improved controllability. 10. Methodological advancements. Introducing a novel approach that explicitly optimizes controllability at the pixel space level, offering a more effective and efficient method for enhancing controllability in text-to-image generation models.
How does the paper address the efficiency issues related to multiple sampling steps in image generation?
The paper addresses the efficiency issues related to multiple sampling steps in image generation by proposing an efficient reward fine-tuning strategy. Instead of diffusing from random noise to obtain the final image, the paper suggests an one-step efficient reward strategy. This strategy involves adding noise to the training images to disturb their consistency with input conditional controls, thereby explicitly disrupting the consistency between the input images and conditions. By performing a forward process on the disturbed images, the model can generate images that maintain consistency with the input conditions. This approach avoids the time and GPU memory costs associated with multiple sampling steps, significantly improving efficiency during the reward fine-tuning stage. Additionally, the paper freezes the pre-trained discriminative reward model and text-to-image model during reward fine-tuning, updating only the ControlNet module to ensure that generative capabilities are not compromised. This strategy allows for effective reward fine-tuning without the need for storing gradients at each time step or performing multiple time-consuming samplings, making the process more efficient and practical in real-world settings.
What datasets are used in the experiments for evaluating controllability under various conditional controls?
The datasets used in the experiments for evaluating controllability under various conditional controls are ADE20K and CocoStuff for the segmentation mask condition following ControlNet, and the Multigen 20M dataset for the Canny edge map, head edge map, lineart map, and depth map conditions. The Multigen 20M dataset is a subset of LAION aesthetics. Additionally, for datasets without text captions such as ADE20K, MINIGPT4 is utilized to generate image captions. The image resolution for both training and inference is set at 512 by 512 for all datasets and methods.
How is the total loss calculated in the proposed method, and what is the role of the hyperparameter lambda?
The total loss in the proposed method is calculated as the combination of the training loss, L_text train, and the reward consistency loss, L_text reward, represented as L_text total equals L_text train plus lambda CDOT, L_text reward. The hyperparameter lambda, plays a crucial role in adjusting the weight of the reward loss in the total loss calculation. By tuning the value of lambda, researchers can control the influence of the reward consistency loss on the overall training process. A higher value of lambda would prioritize the reward consistency loss more, emphasizing the controllability aspect of the model, while a lower value would give more weight to the training loss, focusing on maintaining the original image generation capability. Therefore, lambda acts as a balancing factor that determines the relative importance of controllability through the reward loss compared to the original image generation capability through the training loss in the total loss function.